So welcome back, everyone. So hopefully everyone remembers that remembers most of what we talked about yesterday. So yesterday we covered the basics, like what's Pandas, how do you load it, a few main object classes, a few basic functions for selecting data, inspecting it, cleaning it, rearranging it, things like that. So now today we'll be covering some slightly more advanced topics. We'll start with GroupBy objects, then how to work with complex or user-defined functions, built-in plotting methods just for very quick visualizations of the data, and some advanced topics like things that you would use to prep for machine learning or to help use the native multi-threading. And if we have time, I'll also include a bit of time series functionality. So if anything's going to be cut from, it'll be the time series section. So GroupBy objects, what are these? Grouping is really it's a really handy function for Pandas. What it lets you do is organize and sort your data into hierarchical groups, and then you get to run statistical analyses on different subsets of the data all in one go. You can the full documentation is here. So when it says splitting, applying, and combining, the splitting is the GroupBy operation. And then the applying step is what we'll be talking about next with the more complex and user-defined functions, because this is what allows you to apply different functions to different groups or apply the same function to separate groups simultaneously. And this combining term here just means that, as you'll see a little bit later, most of the functions that you can apply to a GroupBy function, they work on the groups, but what they return is the same shape as the original. They basically return the original data frame without the grouping structure. So you would have to, if you wanted to preserve the grouping structure, you would have to do a GroupBy, apply the function, and then do the same GroupBy all over again. So that's the only drawback. So let me get back to the slides. The syntax is fairly simple. It's just you just call the GroupBy method off of the data frame, and you can give a single column or multiple columns in a list. If you give multiple columns, you just give it a list of the column names as an argument. If you give it a single column name, you still have to, if you're going to use the list syntax, you still have to include the single column name in brackets. So I find it handier just to remember the by equals call. It just makes more sense to me. And if you have to group by rows instead, what you would have to do is take the transpose of the data frame and then do a group by. So aggregate methods and transformation methods, as I said, evaluate each group separately using the same syntax as data frames. And it is possible to apply a different method or function to every group. However, it does get complicated. If you want to select different groups by category name, you use the getGroup function. And instead of a list, you give a tuple, at least if you're giving more than one column or category. If you're getting a single category, you actually still have to give it as a tuple and even include this little comma here. I don't know why they decided to deprecate using a string argument, but it is what it is. Maybe they'll wise up and bring that feature back, because this is a not so intuitive syntax for getting a single category. So One of the things that is made more difficult about group by objects is conditional selection. However, there is a filter function that makes this very much easier. The API is right here. So filter takes a function that it takes a function instead of a direct conditional criteria. So you have to use something like a lambda function in order to use it. So I've loaded the example that was in the web. It creates a data frame where columns B and C are just some numbers, but column A is categorical with two categories, foo and bar, repeated. So if I group by if I grouped, let me do a print statement on this as well. Dagnabbit. Don't like using this keyboard. Oh, that's right, it doesn't print. Yeah, if you try to print a group by object, you'll just get this. So I forgot about that. So what you would actually need to do is do like group head, something like that, which you just get the same thing back. But anyway, so the main data frame is categorized by foos and bars and then some numbers. So if you group by the category A, you get two groups, the foo group and the bar group. And then if you use this filter function, what this lambda x is doing is that it's taking the mean of column B in each group. So for column B, the foo group is you're taking the mean of 1, 3, and 5. And the mean of that is, so the sum is 9 divided by 3 is 3. That means 3 is not greater than 3, so the foo category is excluded. If you take the mean of the bar category, which in column B, which is 2, 4, and 6, the sum of that is 12. The divided by 3 is 4. 4 is greater than 3.
Rebecca, again, they are asking to zoom in.
Oh,
yeah.
Sorry.
Thank you.
Whoops, not quite that far. Okay. So if you take if you plug in column B into the mean function for the bar group, 2, 4, and 6 average to 4. 4 is greater than 3, so it does print the bar group. And that's what you get here. One thing to notice about Jupyter Notebooks is that when you print a data frame without a print statement in a Jupyter Notebook, it formats the table a little bit more fancy. But you can that has to be the last argument in a given cell in order to do that. If I try to do like if I do this, then it doesn't work for this part. So if you have more than one prints, if you want to print more than one thing in one cell, you have to use the print statement for anything but the last one. Okay. So that was a little demonstration of the filter function. So as you saw, you call filter off of the GroupBy object itself, give it a lambda function that evaluates a conditional statement, and then only the groups that return true for all of the elements are included in the output. One of the typical use cases is for removing groups with too few members. And as I noted before, group structure is not preserved in the output. And that's by design so that you can add your results back to the original data frame. I believe I'm going to have you do the, yes. So I had an example or code along where I wanted you to group exoplanets, the exoplanets data frame by the planet type and assign the results to this grouped planet variable. And then I wanted you to print the mean mass for each group. And if you're up to it, call the filter method on the grouped object to remove the planet type group with 5 or fewer members. But as usual, as we discovered yesterday, there was a little bit of a hiccup where I did not clear these prompts. So let me find the day 2. There we go. So one of the things that you can do to skip to this part is you should, and I should have noted this in the slides. I'll note this in the slides for future versions. I'm loading this fixed version of the exoplanets data frame. So that's the version that includes the fixes to the mass and radius columns and the eccentricity column from yesterday. So I'm just re-importing that and then doing the GroupBy and then doing the GroupBy operation on that. So if we run that, then grouped underscore PT is defined. And then if I print the head with argument 3, it prints the first 3 entries in every group instead of the first 3 entries of the data table as a whole. So you can see 3 gas giants, 3 Neptune-like planets, and it doesn't necessarily sort them either. So sometimes you get something like with the super Earth category where it's split across the Neptune-like planets. Then you have the terrestrial, and then you have the unknowns. No, I thought that it normally sorted them, but that's a bit strange. Let me see if that, yeah, it's still doing that. Okay. I guess it just works out that they're organized this way. So now, let's see, I said to do the mean mass. So let's do that. So I will change this to mass underscore ME, change this to mean. And now you can see that each planet type has a mean mass in Earth units. So all much more massive than the Earth, especially the gas giants. That's like multiple times the mass of Jupiter. So if I want to call the filter method on the on this GroupBy object, then what this does is that and then I print if I do X. So I have this set up to as a GroupBy.filter lambda G for a group, and then I evaluate whether the length of the group or the number of entries in a particular group is greater than 5. So then if I and then if I were to type planet type dot unique, now it's giving me 4 groups. And those 4 groups are yeah, and the 4 groups are the value counts. you can get with the value counts. Now you can see that the if I print the original, the planet type for the planet types, the value counts gives 5 categories and 5 numbers, and you can see unknown has 5. If I print the same for the filtered data frame, now we only have 4. The unknown category has been removed. All right, now back to the presentation. Now let's talk about functions. So we already looked at how you apply the basic sort of NumPy style functions for evaluating statistics and things like that for the entire data frame and for one operation at a time. So what if you have multiple functions, or if you want to create a custom function? There are several different ways to do this. If you need to chain statistical functions, one of the recommendations is that you use this pipe function to make it a little bit more readable. I haven't really needed to use this, but it is there if you need it, and it's the very first thing they present in the documentation on this section. So this is also helpful if you have to apply multiple functions that you've defined. So let's say you've got a data frame that does a data frame that includes some city names and country names, and you have and you extract the city names and the country names in 2 separate functions. And then, so ordinarily what you would do is that you would just sort of wrap one function inside of the other. But with the pipe method, what you would do is you would call pipe as a method of the data frame, and as arguments you give the functions that you are applying, and then each time you call pipe, that's the next function it applies. So these are all applied in order. I haven't needed to use this, but it is there if you're really concerned with making your code more readable. And this might actually, like syntax-wise, this actually makes more sense. This is how you would chain regular functions as well. So that's like define functions. So like if you wanted to call if you wanted to calculate the mean of the standard deviation or something, you would call the data frame dot mean or dot standard deviation and then dot mean off of that. That's how you would chain those functions. Now there are other options for applying complex or user-defined functions. If you want to apply functions element-wise, so a function that takes a single element and returns a single element, then you would use the map function. If you want to apply an aggregating function or reducing function, so that those are things like mean and standard deviation that you take a whole set and it outputs one number, then you would use a function like ag. If you want to apply what's called a broadcasting function, which is where you evaluate something over an entire column or an entire row, for instance, but then the output is the same shape as the input, then you would want to use this transform function. And both ag and transform can be applied to GroupBy objects. And if all else fails, you can use apply, and that's to apply one or more functions, column-wise, row-wise, or group-wise, to one or more series in a data frame. So let's go into these in a little bit more detail. Here's an example with the map function. So as I said, the function that map can apply is one that has to take a scalar and return a scalar. You can't have it take in vectors or output vectors. For most operations, it's usually just faster to apply vectorized functions, like if you can use if you can just raise the whole data frame or raise a column to a power, for instance. You can do that. You don't need to use map. But you might need to use map for something like this function that I've created over here, where the conditions change depending on the value of each individual cell. So I've designed this to kind of look vaguely like something you would use to calculate the coefficients of a chemical rate equation. This isn't a real function, it's just made to look kind of like one. So I've defined this function that evaluates differently depending on whether or not the temperature is less than or equal to 0, which is unrealistic, less than 300 but greater than 0, to return one value. And then if the temperature is greater than or equal to 300, it returns a different value. And so then I define the data frame for some numbers that would be suitable for this function. And then I print, well, first I print the original data frame, and then I print the output of the map operation that applies this function. So then the output looks like this. It's the same shape as the input. With aggregating functions, you might use something like, this is something where you would use only functions that take in an array and output a scalar. So that's things like mean, which is what I've applied here in this example. This is overkill. You would rather, it's better to use .mean than .ag mean. But this is just an example to show show the syntax. And this is one where you might use ag if you wanted to apply different statistics to each group. So I believe I have this as an example. Yes, so I have, so here I'm doing a GroupBy. Well, here I'm taking the GroupBy object that we already computed, where it's grouped by planet type. And now I'm applying ag. I'm using ag so that I can apply different statistical functions to different columns. And I'm passing them as the columns to apply the function to as keys in a dictionary, and then the functions to apply as values. So now if I then print, actually, I think what I needed to do was do this. Yes. So that's what the output looks like. So notice that this is because I've applied multiple functions to multiple columns. The output of this is a hierarchical data frame. So I've got the super column, the column names in the original data frame are sort of the top level. And because I applied multiple functions to the mass column, that's these are printed as the second level headers. And then because I applied different functions again to the radius and orbital period columns, those are also printed. Now let us see how that changes if I do this. Now if I only apply one function per column, then it does not print second level headers. It's only because I gave it It's only because I gave it multiple functions for one column that it did that. And let me get back to the problem. Yeah, so I showed an example of how you can pass multiple functions as a list or as a dictionary with the row and column names as keys and the functions as values. You can do similar things for transform. Transform is different because it applies the function to every cell of a data frame and returns the output as in the same shape as the input. You can pass multiple functions the same way in as an ag. So you can give it a list of functions and then print out the result. And you get the multi-indexed hierarchical data frame. And it's important that you not modify your data in place, because otherwise it's important that you not modify the data in place, because then it can it's not clear whether or not it's working on the original data frame or a copy. And then the behavior can become undefined. And if this doesn't work for you, you can use apply. Apply allows aggregating, broadcasting, and even expanding functions. And by expanding functions, I mean when the output is list-like for every cell, so that each cell produces multiple outputs. It is slower than ag and transform, and it may fail to preserve GroupBy objects structure or raise misleading error messages if you do that. But there is one use case, and that is if you have to use a broadcasting function that you might otherwise use transform for, but if the function varies by group, then it's more intuitive to code if you use apply. And that's because transform actually receives the GroupBy objects in two parts. It receives the columns broken up into series, but then it receives the groups again as data frames. But apply only receives the groups. And I have an example of a function with that works with transform, because it applies to all the groups equally. So this is but if I remember correctly, your exercises, I started to set up a function for you that uses apply and varies by group. So you'll get that in your exercises. But here's an example with transform. So this works because it's all the same function for every group, and the aggregating functions that are included in here, they take the same input they take the input the same way that transform does. And so then when you output the so here I'm using the exoplanets data frame, but I'm grouping by detection method this time. So if you want to see grouped to dot head 1, gotta wrap that in a print statement. So well, it would help if I just printed the detection method. Only detection method, because this is a bit excessive. So let's do that. So now you can see there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 detection methods. But then this function is applying it's applying these aggregating functions group-wise but it's applying the function as a whole, since not all of the operation is aggregating. It's applying those to all of the cells. And it's because of this little x minus right here. If I was only printing this part of the statement, then the whole function would be more suitable to ag. But this is a normalizing function, so it is outputting something for every single cell. And then I just printed the describe function so that you can see some of the values that that are produced by this function. So it varies from 0 to 1, and then you see these values are all skew small. Anyway, there's kind of a nonsense scientifically, this is a nonsense example, but it's useful for showing how transform works. You can also do windowing operations. So this is technically, windows are actually sort of like a time-based GroupBy under the hood. And what this does is that what windowing operations do is that they evaluate from whatever the current position is backward up to the size of the window, or if it's a cumulative function, it evaluates backward to the start of the series. All of these methods have a minimum periods quar, which allows you to set a minimum number of valid points in the window. If there are no valid points, then the entire window gives you a nan. And there are 4 different types of windowing operations, and the only one that cannot be used on GroupBy objects is expanding. So let's take, let us follow that. So the windowing operations table is here. 3. Let me see if I can't, you should be able to scroll. There it is. Okay, so you use your scroll, you have to use your scroll bar sideways to view the entire table. But anyway, you have the scrolling one, you have the rolling window standard, the weighted rolling window, which allows you to apply exponential weights. Expanding window is sort of cumulative. Oh, sorry, the exponentially weighted window is down here. The other weighted window allows you to apply different weights. So we already covered this example, so I'm going to skip ahead to the built-in plotting methods. So you don't actually have to apply to import matplotlib if you want to view your data frame data as plots. This is more cumbersome, and it's not really intended to be used to produce publication-ready plots, but it is available if you want to do some quicker visualization. So Pandas provides this plot wrapper method. And for this, you just apply a kind or plot.kind, where kind is a variety of matplotlib plot. The default kind is line, but there are other pairwise functions available that you can view here. So the basic plotting is just, if you don't give it an argument, it just uses the standard line plot. For other options, you have bar and bar H, hist for histogram, box for box plot, KDE or density for density plots, area for area plots, scatter for scatter plots, blah, blah, blah. Okay, so KDE function looks like this. If you're not familiar with KDEs, KDE stands for kernel density estimation. And what it does is that you take a kernel function and you treat usually a Gaussian. In this case, the default is Gaussian, a Gaussian kernel. So you treat every function or every point as a function of this, of the kernel shape, of unit height, and then you sum them all up. And it's sort of like creating a smooth histogram. So it removes a lot of the, it's a good way to avoid binning artifacts. As for area plots, there are also a few other plots that are not included in matplotlib by default, but they're a little bit special, and I've never had to use these, but they're there if you're available, or if they're available if you need them. You can do things like autocorrelations and lag plotting, Andrews curves, which allows you to see some clustering for certain parameters. Let's go back up to other plots. For area plot, the area plot is what matplotlib calls a stack plot. Sorry, tongue-tied. So most of the arguments, or most of the formatting arguments that you would provide to matplotlib can also be applied as quargs of this plot function. So you can give it, you can specify the kind, the X and Y axis labels, the X and Y axis scales, you can label the functions, or sorry, you give it the X and Y here, and then you label the X and Y here. You can give it markers, colors, opacities, you can even specify the figure size. But as you notice, this gets kind of long and hard to read. So it's not the best if you want to distribute this code, or and it's not as good as just using matplotlib if you want to produce publication-ready plots. As I mentioned, it can quickly become unintelligible with the sheer number of quargs. I should also note that log bin scaling is not available for hexbin in this wrapper. It is available for the matplotlib version. And also, you can only call one plot style at a time for all subplots per use of plot. You can pass two tuples of columns as subplots, but then you cannot use scatter or hexbin. And I should also note that in general, most of what you can do with the plot wrapper, and indeed matplotlib in general, can be done better with Seaborn if you're using Pandas. Seaborn is tailor-made to take in data frames and then output publication-ready plots. Things that look like this beautiful figure, or these box plots, which, by the way, both the box plot and violin plot versions of Seaborn are much easier to use than the equivalents in matplotlib. So I highly recommend familiarizing yourself with Seaborn if you plan to use Pandas. I believe this is the last one before we go to the exercise. Yes. So I'm going to do a very quick example with the making a KDE plot of the radius column. And I'm going to set the x-axis limits to 0 and 30. So we already pulled up that website, so I'm going to go straight here to the notebook. And then, so I'm just taking the original exoplanets data frame. I call plot, specify kind equals KDE, y equals radius. So I'm just giving the column name as the y value. And because this is a density plot, then all you really need is the y value. The x value is just the, those are the values that you're plotting this density function for. And then I'm using xlim to set the x limits. So it takes a little bit to compute because KDE is a little bit computationally expensive under the hood. So this is what you get as an output. If I don't include xlim, the one annoying thing about KDE is that because these kernel functions have a very broad extent, then they can go below 0 even if it doesn't make sense for them to, or they can go out to very high values even if it doesn't make sense. So that's why the xlims are important to include if you're going to use this type of plot. Does everyone see this time series slide? Cool. So I think we have the time to get into a little bit about the time series, so I'm going to go ahead and do that. We've been making good time today, in spite of everything. Oh, let me minimize that. So most of the time series functionality of Pandas is most of it is based on similar data types that NumPy includes. So the array classes that you see over here, or sorry, the scalar classes that you see over here, these are the data types these are the data types of the cells specifically. If you use these data types as indices, they become date time index, time delta index, and period index. And the Pandas data types, which are pretty similar to the NumPy data types, are date time 64, time delta 64, and period. So the date times are pretty much what they say. They're timestamps. And they are usually in nanoseconds. Sorry, is there anything? Okay. Thought there was somebody interrupting about not being able to see. Okay. These are typically given in out to nanoseconds, and they may or may not include a time zone. Time deltas are increments from either a starting position or an ending position, and you have to give the number of repetitions or the spacing of the repetitions. And these are also by default in nanoseconds. Periods are a little bit different. They're more like bins. So you treat them like you treat them as if they have as if they're endpoint inclusive bins. So for the date time type, for date time and time delta, you need to specify a starting point, an endpoint, either the number of repetitions or the spacing between the increments. So you need 3 out of 4 of those arguments for each of these. For period, you can give the start, the end, and the number of cycles. You just need 2 out of 3. There's more information here at this time and date series functionality. So I'm just reviewing the data types for these. Most of the functionality is in things like windowing operations, resampling, and other functions that you can apply to this type of data. Let's see the overview. Here's a full table of the classes, types, and their creation functions. You'll notice here there's a date offsets function. I didn't really cover that because it's not really, it's only really used if you have to deal with things like leap years and weekdays and things that are peculiar to calendars. So this is a little bit of a specialty topic. I'm sure it's useful for some of you, but we don't really have the time to get into that. So now let's talk about precision and date ranges. So you can compute a date range with a function named date range, and that will take timestamps and assume integer. That can take either timestamps or integers and float inputs. But if you give it an integer or floating point input, it doesn't raise an error. It interprets those floats or integers as Unix times, and that means that's times since midnight, January 1st, 1970, in nanoseconds. And in fact, all of these date times are stored in that format internally. And for a 64-bit date time, given that the underlying unit, the base unit is nanoseconds, that limits the amount of time that you can actually represent without coarsening the unit. Since they're stored as 64-bit floats, a 64-bit number in nanoseconds is something like 400 years, give or take. Like, it's not quite 400 years, but it's close. So that limits the range of times that you can store. But you can convert to different units using the unit quark to, for instance, convert to whole seconds. And that would allow you to represent dates out to millions of years. But BCE dates are also can also be problematic. So you have to wrap a date time in this numpy.datetime64 in order for timestamp to interpret a BCE date. So in general, if you're dealing with, it may or may not be worth your while to convert to timestamps depending on the resolution of your data. And the Pandas datetime function does not handle series of out-of-range date times. So you have to use an apply function to convert each individual cell in a vectorized function. So those were the caveats, but now let's talk about the cool things that you can do with time series. One of them is resampling. So you can automatically interpolate data from one time series to another with different spacing. You can either upsample or downsample, or or you can also sample to these same increments, but shifted to a different start or end time. Downsampling is simple because to shift or to shift your date times either in keeping the same increments and just shifting them, or downsampling it to coarser resolutions, you can just use the resample function straight. It essentially does a time-based GroupBy. So most aggregate GroupBy methods can be called on the result, just like it's a regular GroupBy object. Resample, all you have to do is give it a unit to shift or downsample. Upsampling is trickier because it requires interpolation. So data at the new timestamps will be nan pretty much everywhere except where they are integer multiples of the old timestamps. So that presents a problem if you say have data on the 15th of every month and you wanted to interpolate to, say, a week. let's say you have data that is collected on the 15th of every month and you wanted to interpolate to a weekly sampling and this is for an entire year. Well, what ends up happening is that, as I recall, the data only line up, they just happen to line up so that there is a data point in like the middle of August somewhere that happens to line up. So all of the data from January up to August is NAN, and then everything after that, then everything after the August date is just a repetition of the date that happened to line up in August. So it's not straightforward. You actually have to do some interpolation, and you have to and it's actually not and that's actually with the interpolation. So what happens, what you need to do first is do something like forward fill, and that fills intervening time steps up to some limit with the most recent non-NaN value. So if you wanted to do a really quick and dirty interpolation, returning to the example that I was talking about, what you could do is set limit equals 1 with forward fill, and that would transfer the data that were collected on like the 15th of every month to the next date, or like to the beginning of the next week that lines up with the 7-day increments. So instead of having like 8 NAN, having like 30 something NANs and then the rest being all the value from August, then you have 12 NANs, or you have 12 values, and then the rest of the 52 are NANs. But now the spacing is even, and you can do the linear interpolation, and that can fill the intervening time steps. So interpolate takes any method that SciPy accepts. So the default is linear, but you could use cubic, you could use spline, you could use quadratic. It's up to you. But yeah, if you wanted to do upsampling, you need to somehow shift the data to points that are actually at that align with the new time steps and then interpolate. So now I will take you to the code along example. I would have asked you to do this if I had remembered to blank the exercise session, but nope, we're going to be doing this. We're going to just do this. Where did they go? Time series. Here we go. All right, so I'm going to start. I start by initializing this time series with this date range. What I want is 10 time steps, 1 second apart, ending on midnight, January 1st, 2025. So this year. Basically, I'm doing the countdown to the new year. So as you recall, it requires a starting date, an end date, or 3 of 4 points. So a start, end, frequency, and periods, I need to specify 3 of those. So I've given it the end so that I can count backwards. And I give the frequency as 1 second. Oh, let me zoom in, sorry. And scooch this over. Let me see, I think I need to rerun that there. So now we have the data are imported. So now I've specified the end, the frequency, and the periods. So the frequency is the spacing of the increment, and the period is the number of increments. So now if I just print the series, this is what I get. It ends on midnight, and then I get the 9 seconds leading up to that. So actually, if I wanted to do the full countdown, it would be 11. So then it's 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Happy New Year. And that's what a daytime looks like. So, yeah, and I posted the solution here. All right, now let's get on to the more advanced topics. Because I think these are the ones that are of most interest to those of you who are using HPC clusters. So if you need to use a program like TensorFlow or PyTorch, they do take series and data frames, but what they need is for categorical variables to be coded as Boolean or numeric values. And there is a Pandas function that makes this very easy. It's called getDummies for dummy variables. So you just call pandas.getDummies, you give it the data frame or series, specify the data type. Usually by default, this is bool, but I believe TensorFlow prefers integers. So you can give it like int4 would be plenty. And then you give it the columns to convert. So for a series, oh, sorry, you cannot apply this to series. So for a data frame df, for some categorical variable v with some in unique values, C1, C2, so on and so on, you can plug in getDummies, then specify you can specify the columns here, or you can specify the columns with the columns quark. But that returns in extra columns for each of the unique variables of for each of the unique values of this categorical variable. Or actually in TensorFlow, typically they prefer you to drop one of the columns if all of the other options are so if there are only 3 options total and there is no other, then you could for the dummy variables, you only really need 2 columns, because if a particular row is 0 for both of those columns, then ipso facto, it must be the 3rd category. So typically they like you to use drop first equals true. And then the dummy columns are output with the name of the by default with the name of the variable underscore, and then they give the actual values that were in those cells appended after an underscore. You can change these, by the way, to be shorter or longer or whatever you want. So you can override the default column names for the outputs, but I usually don't bother with that. And so in these columns, the values will be true wherever the variable equals the category name in that particular column, and false otherwise. Now, as long as we're talking about categorical variables, it's very important to bring up the categorical variable type if you care about efficient memory usage for storing your data. The categorical data type reduces the memory usage of variables by mapping unique values to very small integer codes and storing the codes at the column's location in memory with the smallest possible bit size. And then it stores the dictionary of codes and the representative values somewhere else, but then it only needs 1 copy of each type of that, of each option in the category. So like when I talk about categorical variables, I mean things like species or the sex of an animal or like the country code if for like phone numbers or something. This works best if you have very, very many more data points than you do categories. So, and there are a couple of different ways to do this. For a series of category types, you can just define the series as pandas.series, give the data, and then specify that the data type is category. In a data frame, if you want to convert an existing column to category type, you just set that column equal to itself, and then call .as type category to convert the data type. You can also create a raw categorical data frame with this pandas.categorical function. And then you give it the list of categories, and you can also declare that whether or not those categories are ordered so that you can sort them. It's worth noting, though, that categorical variables only support string vectorized functions. So once you've converted columns to categorical, those are the only functions you can apply to them. But for storage, they're very, very handy. And I will show you, since the example is not cleared, since the example is already included in this code block. So I want to take you back to the exoplanets data frame. And I'm going to have to reload this because I had to reopen it. Where was it? Should be here. So then, categorical data type. So just to remind everyone what the memory usage of the planet type and detection method columns were. That's what the values were. So as you can see, the planet type and detection method columns being strings and object type, they each use about 10 times as much, not quite 10 times as much memory as the numerical columns, like 7 times more, something like that. So, and just to remind you how many unique values there are. So I'm going to do that, value counts. So you've got, there's 5 categories in the planet type. And there's, I believe, 11 in the detection method. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, 11 categories in the detection methods. Anyway, so you can see, again, look back up here at the memory size of the planet type and detection methods. Now, watch what happens after I've converted them to categorical type. Now not only have they been reduced substantially, now they occupy like 10% of the size of the numerical columns. So their total data usage has been reduced by a factor of like 50. Several tens at least. So this is very important if you have a lot of categorical data to store. But there is a limit, and that is if you have, I think it was about 50% of the length of the data frame. If the number of categories approaches like 50% of the length of the data frame, then you actually start to use more memory by converting to categorical data type than you do by leaving it alone. So this is mostly useful if you have a categorical data type that is with a relatively small number of unique values. Now, another reason that I went into the categories a little bit is because that also translates to some of the information translates well to these cut and qcut functions. this is where it makes sense to have labels or for the category labels to be ordered. So there are functions that allow you to bin numerical series data, like for age brackets or something like that. And that allows you to convert to categorical variable types. And then you can assert that those categories have an order. So there's a cut that lets you provide either n equal number of bins or an array of variable bins and optionally labels for each bin. If you don't specify a label, then it will just give it'll just use the starting and ending points as the labels. If you set right equals true, then that makes the bins half open on the right. If you have if you have right equals false, both bin edges are excluded. So this is a little bit peculiar. It's not like bins in NumPy histograms. So the default is for both bin edges to be excluded, not for it to be half open on the left. Q-cut is pretty much the same, but it does Q quantiles, so like percentiles. Percentiles converted into a decimal. Q can be an integer or a list of right and left edges. And so if you look at these cut functions, then by default, actually the cut functions are assert that these bins are ordered. And so that means that if you plot them or if you do if you evaluate mathematical binary expressions, then they will evaluate as if they're in order. And they will that also allows sorting. There's another way to save some space with sparse arrays. If you have a data frame where most of the data is nan, or not a number, or not a time if it's timestamp data, you can store them in sparse array. Whoops, wasn't trying to click. You can store them in sparse arrays. So this is based on the SciPy sparse array type. So you can initialize series or data frames as sparse D type with the quard D type equals sparse D type. And then you can also you can sort of sub data type this, because sparse D type itself has the D type argument for quard. And that lets you specify the precision. So like float 64 or like, I don't know, int 16, something like that. And you can even specify a fill value. The default is for it to just be nan, but you can specify something like a 0 or a -1. And that just determines what is displayed when you print it out. When it's stored in memory, it stores like one copy of that fill value, and it only renders that fill value in all of the empty spaces in the when you print it out. In memory, it just stores like a single bit switch at those locations to indicate whether or not that cell is empty. If you've already defined an array and you want to convert it to sparse type, you can just call it the asType function, just like for categorical variables or other memory saving variable types or data frame types. And there's more information here in the in the documentation. So there is, if you want to do calculations with this type of data, there is a sparse accessor that's similar to the .dt accessor for datetime objects, and the .cat for categorical objects, and the .string for string objects. These accessors, what they do is that they let you sort of index into the data that's in a specific cell and operate on it. as if it's sort of its own separate thing. Like for a string, for a regular string, you would only have to you could just call the string operation straight off of it. But when the string is embedded within a data table or a data frame, then you have to use like the string accessor in order to index into that string. The sparse accessor does the same thing for sparse data. And the .dt accessor for datetime objects allows you to like extract the unit in the hours place, or the value in the hours place, or the value in the seconds place, things like that. That's what accessors do. So let me go back here. Okay, now we get to the more complex stuff, the pivot and hierarchical data frames. I'm not going to spend much time on this because these get to the point where they're, at least in my experience, these tend to get really unwieldy to actually handle. They're just good for displays. So if you want to use if you have a lot of categorical variables, it might be efficient to reshape the data frame with pivot, and you give it the rows if there are repeated row indices, and then, or more often, you just give it the columns that are where there are a lot of repeated rows. Oh, sorry, the indices are the indices and the columns are the sort of the output values that you want to, it's what you want to use as the rows and the columns. So the columns, typically this will end up being the top level row. So let's say you have this data frame that I've just labeled more junk because I keep myself humble by labeling stuff as junk and dummy and stuff like that. So it's indexed 1 through 5 or 0 through 5. It's got a foo column where the values are strings 1 and 2. There's a bar column that's just repeated ABCs. And then there's unique values in this Baz and Quux columns. But there's a lot of repeated values in the foo and the bar column. So now you can do a pivot, set the indexes equal to foo and the columns equal to bar, and then what you get is that, so then foo becomes the index. And so every value that has a foo value of 1, so that's this top half of the data frame, that gets grouped together, and then the bar columns become subscripts of the or sublevels of the Baz and Quux columns. And it looks like this. But the result is a hierarchical data frame, and as I've mentioned before, hierarchical data frames get to be really unwieldy to index. And so they use multiple indexes. In practice, you can use tuples to index into these multi-indices, but you have to be careful that you know what levels you're working on and what levels each headings are on. And that's if you can't actually look at your data frame, then it can be that can be tricky. And it gets much harder if you want to try and actually do operations on these. So I usually avoid using anything that converts to hierarchical data frames, but that's my preference. If you find them more intuitive, you're welcome to work with them. And as I said, pivot table might save you some space. All right, the last thing I want to cover is that there are some there are some native parallelization features for if you want to do like MPI, so communicating across nodes, those require additional modules. But there are some built-in functions that allow parallelization of column-wise operations. And the easiest one is using numba. Now, numba is a separate module. So if you're using a pip, a pip distribution of Python, you'll have to import that separately. If you're using the Anaconda version, that's included. So what you do is that if you have a column, a vectorized operation, like anything that you would plug into a .ag or .transform function, if it's a built-in function specifically. So then you can use, there's a quad called engine, and then you give it numba, and then you specify engine quargs and give it a dictionary that says parallel and or that has the key parallel and the value true. And that makes the function use automatic multi-threading to handle each column with a separate core all at the same time. There are some caveats. When possible, use the same number of threads as columns. And never ever use more threads than there are columns, because that will actually use more memory than not parallelizing at all. Essentially, you're oversubscribing and sending the data to, essentially what that does is that it copies the data to extra cores that then sit idle. So you don't want to use more threads than there are columns that you're processing. If you're more experienced, you can write your own just-in-time compiled or Cython functions that can be used with numba. And those are detailed in the enhancing performance section of the documentation. So you can write your own functions that have this @JIT decorator, and then you'll be able to use the numba quark. So I believe there's an example down here somewhere. Yeah, here. So you import numba. The very first thing you set is the number of threads. This is actually useless, setting it as to 1. So you want to set it to 2 or 2 or more. So for a rolling mean, for example, let's say you have this random data frame and you want to take a rolling mean of over 100 samples at a time, and it's got 10,000 entries. So then the rolling mean would work like this. So you take the df.rolling.mean, and then you'd set engine equals numba, and then the engine quargs parallel equals true. And if there's 2 threads, so let's say the basic rolling mean takes 0.34 seconds. And then the number version that uses 2 threads, it doesn't quite cut it in half, but it does cut it by about 50%. The reason it's not completely cut in half is because there's a little bit of overhead. And I believe I have an example coming up. Should be either on the next slide or the slide after. There's also support for chunking, which is loading and working with subset of data. That can be done with Apache Parquet input files, JSON input files, and PyArrow chunked arrays. So let's see, does that go to the, no, that does not go to the Pandas documentation, that goes to the Apache documentation. There's also expressions with eval. I mentioned this briefly at the beginning. If you use pandas.eval, then you can use the num expression operator, not engine, not operator, engine. And num expr is actually included in the SciPy bundle. So that you shouldn't have to install anything else. And that can do a little bit of, that can give you a little bit of acceleration too. Now, if you want to follow along with this, then you would need to restart your Jupyter notebook with a different number of threads. Okay, so since I'm going to be running this as a shell script, I needed to comment out the lines that are used in Jupyter. So these time it lines with the percent decorators, those only work in Jupyter. Otherwise, you have to load time it in OS separately. So I'm setting the number of threads. And I happen to know that it's going to be 6 because I'm giving this array 6 columns and I want to run this parallelization operation over all of them. So I'm creating this random data frame, 250,000 elements, 6 columns, labeled A through F. I print out the data to the output file. I specify a number of loops and a number of repeated iterations in order to be consistent between the two runs, so that we're comparing apples to apples. Then I record the serial times by using this time it repeat function. I put the rolling mean function in quotes. Yes, I see it. Should the 8th line be commented? No, the 8th line, yes, the 8th line does need to be commented because this is something that you would set in the Jupyter notebook. Here, I'm setting it with the number of tasks that I'm going to give it in the shell script. So it should have been in here. So the number demo looks like this. And so here, I'm going to set CPUs per task equals 6. And then you would have to adapt some of these parameters to your own cluster if you're on a different cluster. And I'm going to change LU test to LU 2025-2-72, I believe was our, I believe that was the, 2-72. Okay. So leave it for 5 minutes. That should be plenty, way more than it needs. Give it a job name, give the output and error message files their names, and then this %J for the job number. Then I set the CPUs per task. And this is what I'm using to determine the number of threads, or to set the number of threads in the code. That's what this line is doing here. I'm using OS to get the environmental variable slurm CPUs per task, and then feeding that into numba as the number of threads. So in order to make sure that I'm setting it right, I'm actually setting the number of columns out here. Okay, so back to the code. This is the standard line. I'm just evaluating stuff.rolling mean with a window size of 500. And I have to pass this globals stuff equals stuff in order for this quoted statement to be evaluated. Otherwise, for whatever reason, time it does not recognize this variable. And it's the same thing with numba, except now I'm adding the to this mean argument, or to this mean function, I'm adding the argument engine equals numba, engine quargs, and then the dictionary with parallel as the key and true as the value. Give it the number of loops, and the globals, again, I got to give it the stuff array, otherwise it doesn't know what variable I'm trying to use. And then I print the times. And then, so here I'm just loading all of the modules that I need. I load the FOSS toolchain usually because if you have to import SciPy bundle or anything more than that, you might as well import the entire toolchain. It's just easier. And then you don't get surprise errors for, oh, this dependency is missing, even though module spider didn't list it explicitly. So I'm saving that. Now I'm going here, and all I'm going to do is cd documents / pandas exercises, And now I'm going to do sbatch, and then the name of the sbatch, numadivo.sh. So now it's got its job number of 1425588. It'll take maybe a couple of seconds to run. And if I reload, there's the output. So this just has a little warning message. This is pretty much irrelevant. Here's the output. So the cat0 copied the shell script itself here, but and then I printed the data frame. Well, I didn't print the data frame. I printed the information about the data frame. So then the mean serial code time was 24 milliseconds, or 25 milliseconds rather, and the number code time cut that down to 3.5. So big savings. Now I can show you, I had some previous runs with more and fewer numbers of threads. So let's see, this one was 4. That also cut down the time, but not by as much, because there were still fewer threads than there were columns. And one of these had, so let's see, it was 4. One of these I used, yes. So for this one, I set 8 CPUs per task, and I believe, and so now you can see that not nearly as much savings. And for some combinations of, or for some sizes of data that I tested, the number code time actually was more than the mean serial time. Okay. So you could have run the shell script on your own computer, or on the if you're on a cluster. I gave the shell script and the raw code file. So you don't necessarily need Jupyter for that. Okay, we're a little over time, but let's go ahead and wrap up. So this is what just to remind you, this is what all we covered. If you have any questions at all on any of these topics, you're welcome to ask now, or if you think of more between now and the exercise block, which will start in about 15 minutes, you're more than welcome to ask.